Good morning to all. Welcome to the channel Firjan. See, today's concept is electrostatic potential and capacitance. In this lesson, it's belong to second lesson in 12th standard. In this one, we discuss electric potential due to charged spheres. Electric potential due to charged spheres. Previous video, we discuss relation between electric potential and electric field. What is the relation? So what are the problems that all we discuss? In this lesson we discuss electric potential due to charged spheres. Electric potential due to charged spheres. See here we have charged spheres. Spheres we have two types is there. One is hollow spheres. We call it as a shells. Another one is solid spheres. Solid spheres. See, hollow spheres again we have two types is there. What another one? Conducting hollow spheres, non-conducting hollow spheres. Non-conducting and conducting hollow spheres. Non-conduct is nothing but insulating or insulators. Insulators. See, or we can write it as dielectric. Dielectric hollow spheres. See, same solid also we have conducting and non-conducting solid spheres. Non-conducting solid spheres. See here, spheres na charged spheres we have two types is there, hollow or shells, conducting, non-conducting. Another one is solid, conducting, non-conducting. Hollow is nothing but shells, so there conducting, non-conducting. Non-conducting, another name is insulator or dielectric. Solid na here conducting, non-conducting. In this one, hollow conducting, non-conducting and solid conducting have same property. What is that property now? Charge will be resides on surface of the sphere. Surface of the sphere. Hollow conducting, hollow non-conducting and solid conducting spheres. Charge always resides on surface of the sphere. See, for example, here it is hollow conducting or non-conducting, solid conducting. Charge will be on surface. So surface will be resides on, charge will be resides on surface. This is the same common property for hollow conducting and non-conducting solid conducting sphere. See, I write here hollow conducting and non-conducting. And another one solid conducting. These have charge resides on surface of sphere. This is the common property for hollow conducting, non-conducting and solid conducting sphere. Solid non-conducting, solid non-conducting na charge will charge in whole, charge in whole sphere. See, this is the difference between hollow conducting and non-conducting, solid conducting and solid non-conducting. In solid non-conducting, charge will be inside is there, whole sphere. But hollow conducting and non-conducting, solid conducting spheres, charge resides on surface of the sphere like this. For solid non-conducting, na, see, solid non-conducting, see this one, charge will be on surface, in surface totally, total volume. See, like this charge will be distributed. Yes, na? So this is the difference between hollow conducting, non-conducting, solid conducting and solid non-conducting. It is for these three. It is for solid non-conducting. It is for hollow conducting, non-conducting and solid conducting spheres. It is solid non-conducting spheres. Yes, now. So about this, how electric potential produces inside, outside the sphere. So that we discuss. Yes, now. See, first one we discuss hollow conducting, non-conducting, solid conducting spheres we discuss. See here, first we discuss electric potential. Electric potential due to hollow conducting or non-conducting. Non-conducting or solid conducting sphere. Solid conducting sphere of radius r at r distance, small r distance from center, inside or outside sphere, inside sphere or outside sphere. What is the electric potential that we want to find out? See, once electric potential due to hollow conducting, non-conducting or solid conducting sphere at all distance from the center. So why we write hollow conducting, non-conducting, solid conducting? Na, this have same property. What is that property? Na, charge resides on surface of sphere, surface of sphere. Whatever the charge is there, that will be resides on surface of sphere. That's why this all will be taken in one case. See, first case. See, case 1. What we can write now? Outside point. Outside point. What is the electric potential? What is electric potential? Before we can discuss, so what now electric potential? See, due to point charge, what is the electric potential at all distance now? See, at this point, V equal to KQ by R. It is the electric potential due to point charge or distance. Here with sign means positive na positive we can write, negative na negative we can write. So electric potential at a point means here due to this point charge, what is the electric potential at point or distance from the charge? See, V equal to KQ by R with sign. So plus means plus we can write, minus means minus we can write. See, now we discuss outside point of the hollow conducting, non-conducting or a solid conducting sphere. See, for example, here it is the hollow conducting or non-conducting or solid conducting sphere. Charge how now it is outside the sphere. Here see, outside the sphere charge resides on outside the sphere. See, its radius is capital R. Its radius is capital R. What now here? Or distance from the center, outside point, or distance from the center, this point, what is the electric potential? So that we find out. For defining or deriving electric potential, definitely we want 2 points. So that's why we can select one point is at infinity. Here to here to here, charge is moving. Here we can find the what is the electric potential. See, for that we have the relation. What is the earlier video we discussed relation between electric potential and electric field with displacement. So that's one. See here, delta V equal to minus of integral E dot dr. This relation we can use. Here see, where to where is charge moving? Infinity to P. Interval is here, we can take infinity to P E dot dr. So delta V equal to minus of integral infinity to P E dot dr. What is the electric field? So E means here electric field. What is the electric field now? Here, this point. at P point. What is the electric field now? E equal to K Q by R square. It is we discussed before videos. Yes, na? So what is the electric field now? E equal to K Q by R square means due to point charge or distance at a particular point. What is the electric field now? So EP equal to KQ by R square. It we discuss in electric charges and fields lesson. With brief information we give. Yes, now see just here due to this point charge, what is the electric potential at this point or distance from the point charge is kq by r square. So that we can write here. See, in this case delta v equal to minus of integral infinity p point. What is the distance here r? We can write here r. E means k q by r square dr. Kq by r square dr. See now here Kq is constant, we can write outside. See delta V equal to minus of minus of Kq constant outside infinity to R 1 by R square dr. See once here integral 1 by R square dr equal to what is the formula now? Minus 1 by r. We discussed already previous also, or otherwise you listen once. See r power minus 2 we can write dr. See here r power minus 2 plus 1 by minus 2 plus 1. So from that we can get 1 by r. So means integral 1 by r square equal to what we get now? See 1 minus 1 by r. See that we can write here. See delta v equal to minus of kq minus 1 by r. Interval is here infinity to r. Infinity to r. See delta v means where to where charge moving infinity to p point. Means we can write here Vp minus V infinity. What is the potential at V infinity na? 0. So we can write, so potential at P means particular point or distance from the center. What now here? Minus KQ. Here upper limit we can write first minus 1 by r. Later lower limit minus of minus plus 1 by infinity. What we get now here? See infinity is 0. 1 by infinity is 0. So we can write potential at P equal to minus of KQ, minus into minus plus. So KQ by R. It is the potential at point P or distance from the center outside the point. Or distance from the center outside the point. Again listen once here. See electric potential due to hollow conducting and non-conducting or solid conducting sphere or distance from the center, inside point or outside point. First we discuss outside point. Outside point means from center or distance, this point. For defining electric potential here or deriving electric potential at this point, what we can take one more point, that is at infinity. So here to here charge is moving, this case some work is done. So that for that electric potential and electric field relation we know, that is delta E V equal to integral E dot dr. See this relation is variable displacement. For that case what is the potential and electric field relation now? Delta V equal to minus of integral where to where? Infinity to P. So that's why we can write infinity to P E dot dr. E means electric field due to charge. So that is KQ by R square. We know already, we discussed in previous lesson. So with brief information, so what is KQ by R square? We can write instead of E, we can write here KQ by R square with dr. See integral infinity to, so P point means all distance, we can write R here. KQ is constant outside, we can write minus KQ. So 1 by R square. So 1 by R square dr. Integration is minus 1 by R. I write here minus 1 by R. So interval infinity to R. First upper interval, later lower interval. See 1 by infinity is 0. We can write potential at P. Delta V na here to here. So means Vp minus V infinity. Infinity 0. So Vp equal to potential at P equal to minus KQ minus 1 by r plus 1 by infinity. Infinity is 0. See what potential at P equal to minus into minus plus KQ by r. It is the electric potential due to hollow conducting, non-conducting or solid conducting sphere or distance from the center at outside point. Outside point. See on surface now case 2 on surface means small r equal to here capital R. So that's why we can write electric potential at surface. We can write it as KQ by capital R. It is the electric potential due to hollow conducting, non-conducting or solid conducting on the surface, capital R distance from the center, that is Vs equal to Kq by capital R. It is on surface, on surface. So next one is inside point. So we discuss. See here, inside point, it is the sphere. Yes, it is the sphere. See, charge is distributed on surface. Charge resides on surface of the sphere. See this case, it is the radius or distance from the center inside this P point or distance from the center. See, for deriving electric potential at point P or distance inside the hollow conducting or non-conducting solid conducting sphere from center, what now we want one more point. So for that what we can do now, here just below the surface one point we can select, that we can take here S. S means here just below the surface, just below the surface one more point. Charge is moving from here to here, charge is moving from here to here. In this case we have to do some work, so that work here we can write Vs means S to P. So that case we can write here delta V equal to minus of integral E dr, E dot dr. See where to where, S point to P point, S I write here P point. See again, for defining or deriving electric potential inside the sphere at or distance from the center at point P, we want to select one more point that is just below the surface, that is we can take it as S here. From S to P charge is moving, that case we get that electric potential. So that electric potential and electric field relation is delta V equal to minus of integral S to P. What is initial point is S, final point is P, S to P we can write E dot dr. So delta V means Vp minus Vs, Vp minus Vs equal to, so S means here just below the surface means radius capital R. So P means small r. So we can write here minus capital R to small r. E means we know already KQ by R square dr. We can take here. Sorry, E. 1 minute. See, electric field inside the solid sphere means solid conducting or a hollow conducting non-conducting sphere na zero. Sorry, not KQ by R square. So what is the electric field inside the hollow conducting, non-conducting or solid conducting sphere? Zero. So electric field inside the sphere is zero. So that's why we can take here integral R to capital R to small r, 0 into dr. So 0 into dr means 0 we can get here. See, potential at P minus potential at S equal to 0. So S will be changes to that side. We get here potential at P equal to potential on surface. What is the potential on surface? Due to hollow conducting, non-conducting or solid conducting sphere, KQ by capital R. From this we can write, see, I write here, shall I erase this? See, what is now here potential at P or distance from the center inside the point is, see here, Vp equal to K capital Q by R. It is the potential inside point. Again listen once here, see, it is inside point, not outside point, inside point, inside point. See here, it is the hollow conducting, non-conducting or solid conducting sphere. Charge is resides on surface. See, it is the capital R means radius of the sphere. So small r now or distance from the center inside point at P. See, for deriving electric potential at point P we can select one more point, that is just below the surface S. See, S to P charge is moving, that case electric potential and electric field relation is delta V equal to minus of integral S to P E dot dr. S means here just below the surface point, that is capital R. P means R distance from the center inside point, so that is small r. See, R to R electric field inside the hollow conducting non-conducting solid conducting sphere is 0. It will discuss in electric charges and fields, we know that one. See, 0, so means integral 0 means 0 we get. So potential Vp minus Vs equal to 0. Vp equal to potential at P equal to potential at S. S means surface. So what is the potential at surface? Kq by capital R. See, potential at surface is Kq by capital R. So means potential at P or distance from the center is Kq by R. So means from that what we know na, electric potential is from center to surface not changes, it is constant. So whatever the potential at surface, same potential will be maintained from center to surface. That is what here na, potential at P inside point is Kq by capital R, on surface also Kq by capital R. Outside point is, it is inside point, it is on surface. What is the potential inside point now? Potential outside point, sorry, Kq by small r. It is the potential due to hollow conducting non-conducting solid conducting sphere or distance from the center outside point. It is outside point, outside point or distance from the center. See here, outside point Kq by small r, it is variable, it is variable according to distance it changes. Here it is constant, from center to surface it maintains same value. So that is inside point is constant, outside point variable, on surface this one. For this we can draw the graph. See here, see, it is the x axis, it is y axis. On y axis we can take sphere, it is a solid conducting sphere or hollow conducting non-conducting sphere. See here, this distances we can take here, it is small r equal to capital R, means on surface it is small r less than capital R, it is small r greater than capital R, means outside point, it is outside point, it is surface, it is inside point, inside point. See now here we can draw the graph from center to surface, it maintains constant. See here, from center to surface, see potential at P inside point, what na, Kq by capital R, on surface Kq by capital R, outside point Kq by smaller, means R value increases, V value decreases. So means it's variable. See, from center to surface it maintains constant value. After that, see, it is decreases, means V proportional to 1 by R, V proportional to 1 by R. It is the graph for outside point, it is variable. Here potential at center to surface is, it maintains constant. So that is Kq by capital R. It is the graph between potential and distance for hollow conducting non-conducting solid conducting spheres. Yes na. See, next one we discuss electric potential due to solid non-conducting spheres. I write here, see, solid non-conducting spheres. See, electric potential due to solid non-conducting sphere of radius capital R at or distance from the center, inside point, outside point. Here charge resides on not sphere, charge in whole sphere, in whole sphere charge is distributed in whole sphere. For this we can find out what is the electric potential outside point, inside point, on surface. We discuss that one. Yes na. See once, I take here solid non-conducting sphere, solid non-conducting sphere. In this solid non-conducting sphere, charges will be in whole sphere. See, like this is their charges. It is the charges. See here, it is the center. From center to surface is, it is the capital R. See, from center or distance outside point at point P, what is the potential? So that we can derive. For deriving that, what we can write now here? See, we can select one more point, that is at infinity. It is outside point, outside point, see, or distance from the center, see, infinity. So charge is moving from here to here. Here in this case we have to do some external work, so we get the electric potential. So in this case what we can take now here, electric potential and electric field relation we can take and derive the electric potential at point P. What is the relation between electric potential and electric field? Na delta V equal to integral E dot dr. It is for variable displacement is there, that case we can take this one. So delta V equal to minus of integral E dot dr. Where to where it is moving? Infinity to P point. I write here infinity to P point, E dot dr. Delta V equal to minus of integral infinity to P E dot dr. Electric field na, what is the electric field? Now means here K q by r square. It is the formula for electric field outside point. So means due to point charge, so it will be act as like point charge. And now so that's why we can take E equal to kq by r square. See, instead of this we can take delta V means where to where moving, infinity to P. We can write here Vp minus V infinity, that equal to minus of integral infinity to P. P means r distance, so that's why we can write r. Electric field na kq by r square dr. See, kq we can write outside, yeah, integral infinity to r 1 by r square dr. We know already integral 1 by r square na. See here minus 1 by r, minus 1 by r. Here we can take, see, V infinity is 0. So what we can write, potential at P outside point. See here, potential at P outside point equal to minus kq. Here we can write minus 1 by r square dr integration na, minus 1 by r, interval is infinity to r distance. See, minus kq, upper interval first, minus 1 by r, later lower interval, minus of minus plus means 1 by infinity. So 1 by infinity is 0. So we can write here potential at P is minus into minus plus kq by r. It is the potential due to solid non-conducting sphere outside point or distance. So kq by capital R. I write here potential at P outside point is kq by small r. It is the potential at P or distance from the center for solid non-conducting sphere. See, for example, on surface we can write, on surface means here instead of small r we can write capital R. See, we can write what is the potential on surface now, Vs equal to kq by capital R. It is the potential on surface of solid non-conducting sphere. It is outside point, it is variable, on surface kq by capital R. Now we discuss inside point. Inside point, see, inside point means, see here, see, outside point here, inside point I write inside point. See here, so this is the solid non-conducting sphere. So charge is in whole sphere. See, charge in whole sphere. So like is charge distributed, yes na. See, it is the center. So what we are doing now here, so from center or distance at point P, what is the potential? So that we can derive. For that what we can do now, we take one more point that is just below the surface, just below the surface we can select one point, that is S. From here to here charge is moving, so that case we can define. See, it is the capital R radius of the sphere, solid non-conducting sphere. It is smaller inside point from center to at particular point P. For that we can take S is the another point which is just below the surface. So that case, so what is the relation now here? Delta V equal to minus of E dot dr, integral E dot dr. Here see, where to where charge moving? S to P. So we can write here interval is S to P. E electric field inside the solid non-conducting sphere na K capital Q small r by r cube. It is the formula for electric field inside solid non-conducting sphere. It we discussed in previous lesson, electric charges and electric field. There we discussed, that's value we can use here. See, E equal to, briefly we discussed there, see E equal to KQR by R cube. Instead of this we can write electric field, we write this value. See now here I write here delta V. Delta V means final point minus initial point, so means Vp minus Vs. See here I write potential at P minus potential at S, so that equal to, see here, minus of integral. S means capital R, P means small r, E means here we can write KQR by R cube into dr. See, KQ by R cube is constant. See, I write here minus KQ by R cube is constant. Constant. We can write here integral or capital R to small r dr. See, it is Vp minus Vs, potential at surface. Yes na? See, now see here K cube by R cube, integral R dr means R square. I write here, see, integral R dr equal to R square by 2, R square by 2. Here see integral R dr. So what we can write now here, potential at P minus potential at S equal to K minus KQ by R cube into R square by 2. What is the interval now here? Capital R to small r. Capital R to small r. So we can write upper interval first, later lower interval. I write here, see, minus KQ by R cube R square by 2 minus capital R square by 2. It is the, first we can write upper interval, later lower interval. So we get this value. See, potential at P minus potential at S equal to, we can multiply here, minus of KQ by R cube R square by 2. We can write KQ R square by 2 R cube, minus into minus plus KQ capital R square by 2 capital R cube. See here R square R cube, 1 we can have. So R square cancel, 1 is there. So what we get now here, see, potential at P minus S equal to, I write here first positive value, KQ by 2 capital R minus KQ small r square by 2r cube. Here see, potential at P minus potential at surface. So potential at surface is due to non-conducting solid sphere na KQ by R. I write here Vp minus KQ by R. It will be changes to that side, means plus we get. So KQ by 2R minus KQ R square by R cube. See, it will be changes to this side. So potential at P equal to KQ by 2R plus KQ by R minus KQ R square by R cube. See, this KQ by 2R, KQ by R, LCM is here 2R. So 2R means here 1 only, here 2. So totally what we get? Here 2 will get 2 KQ, KQ means 3 KQ by R minus KQ small r square by R cube. This is the potential at point P. See, I write here potential at P is 3 KQ by R minus KQR square by 2R cube. This we get here na 2R cube, 2R cube. This we get KQ by R common na, what we get na here 2R, sorry, here 2R also, here 2R, here 2R, here 2R cube. See 2R we get. So what we get now finally, potential at P equal to KQ by R common na, here we get 3 by 2 minus of R square by small r square by 2 R square. It is the value we get. So means this is the electric potential at point P or distance from the center inside point KQ by R 3 by 2 minus of small r square by 2R square. So this is the value. See once again here it is the solid non-conducting sphere. Charge will be in whole sphere is there. This case or distance from center at point P. For deriving electric potential at point P inside point, we can select one more point that is just below the surface, that is S. From here to here charge is moving, that case displacement is changes variable. So that case what is the relation between electric potential and electric field now? Delta V equal to minus of integral E dot dr, where to where, S to P, S to P I write. So electric field inside non-conducting solid sphere na E equal to KQ or small r by R cube. It is we derived briefly in electric charges and electric field lesson. So we remember here what is the electric field due to solid non-conducting sphere inside point. So that is KQR by R cube, that we can use here, KQR by R cube. See KQ by R cube is constant, we can write integral R. So R to R small r dr, small r dr means so R square by 2 we get. So upper interval first, later lower interval, KQ by R cubed minus R square by 2 capital R square by 2 minus capital R square by 2. We can multiply now here, see KQ small r square by 2 R cube, minus into minus na plus KQ capital R square by 2 R cube. So R square cancel, 1 is there. See we can write potential at P minus potential at S equal to KQ by 2R, here it will write later. So minus KQ R square by 2 R cube. In this one see potential on surface is KQ by R, it will changes to that side means plus we get, that I write KQ by 2R, KQ by R, LCM is 2R. So here we can get 2 KQ, here KQ, 3 KQ by 2R minus KQ R square by 2 R cube. See in this one KQ by R we common now here 3 by 2 minus small r square by 2 R square. It is the electric potential due to solid non-conducting sphere or distance from the center inside point, inside point. For example here if x r equal to 0 means at center, r equal to 0 means small r equal to 0 means at center. What is the electric potential? See electric potential at center equal to, instead of r we can write 0, this total term 0 we can get. So what we get here 3 by 2 KQ by R we get. See potential at C, potential at C equal to center 3 by 2 we can write potential on surface, we can write this is the relation. Why? Because KQ by R is potential on surface due to non-conducting solid sphere. So means potential at center equal to what we can write 3 by 2 potential at surface. So this is the electric potential due to solid non-conducting sphere of radius capital R. See we can draw the graph for this. See for that I write here all the points one by one. See what is the potential outside point, it is outside point, outside point. What now here potential due to solid non-conducting sphere outside point or distance, what now value K Q by small r. Potential on surface, surface is KQ by capital R. Potential inside point, inside point or distance from the center is KQ by capital R 3 by 2 minus R square by 2 R cube. It is the potential inside or distance from the center for solid non-conducting sphere. Potential at center now 3 by 2 times potential at surface. These four are the, it is outside point, it is on surface, it is inside point, it is at center. We have four values is there. Electric potential due to solid non conducting sphere, outside point is kq by r. Electric potential due to solid non conducting sphere, on surface kq by capital R. Electric potential due to solid non conducting sphere, inside point, that is kq by r, 3 by 2 minus of r square by 2 r cube. At center 3 by 2 Vs. For this we can draw the graph. Yes, na? See, we can take potential on y axis, potential on y axis, distance on x axis. Here we can take distance, it is r greater than capital R, it is r less than small r, capital R, it is small r equal to capital R. See here, it is y axis, potential here we can take, it is the solid non conducting sphere. See, at center it is some value is there, that is what, 3 by 2 times potential on surface. Potential at center equal to what, 3 by 2 times potential on surface. See, it is maximum is there, after that what now its value, see, it is now its value is changes, it's now up to this changes. After this point what now this one, it will again exist. This is the graph, v proportional to 1 by r here, here v equal to 3 by 2s, here now see, inside point v p equal to k q by r, 3 by 2 minus of r square by 2 r cube. It is the graph for solid non-conducting sphere. Electric potential due to non-conducting sphere. Here to here decreases. Again it will be inversely proportional. So this is the graph for electric potential due to solid non-conducting sphere of radius capital R. Okay na? See, next we discuss a charge Q, capital Q is distributed over two concentric hollow spheres. So that case, what is the potential at center of the sphere, we find out. See, what now here, see, charge Q, a charge capital Q is distributed over two concentric spheres, two concentric hollow spheres, two concentric hollow spheres, hollow spheres of radius of radii smaller and capital R is greater than small r, such that their surface charge densities are same. Their surface charge densities, charge densities are same. Then find electric potential. See, electric potential at the center of the, at center we want to find out. So this is the problem. See here, what is the problem now here? See, a charge capital Q is distributed over two concentric hollow spheres of radii small r, capital R is greater than small r, such that their surface charge densities are same. One condition they give, surface charge densities are same. Then find the electric potential at the center of the concentric spheres. See here, we can take here concentric spheres, it is one, see, it is the other one. See, these are concentric spheres, it is the center, it's at center point, what is the electric potential, so that we want to find out. For that, here see, It is smaller, it is capital R, it is the radius. Yes na, radius of inner sphere is R smaller, outer sphere is capital R. These are the concentric hollow spheres. See, total charge what they give, capital Q, so that will be distributed over concentric spheres. For that we don't know what is the value. First one is Q1 we can take, second one is Q2 we can take. What is the total charge now? Q1 plus Q2 equal to capital Q. It is the charge. It's we can take it as equation 1. See here, here we can take. So next here, see what they give condition such that their surface charge densities are same. Surface charge density means surface charge density sigma equal to charge per unit area, charge per unit area. So this is called as surface charge density. Here surface charge density of A sphere and B sphere are same. See, we can write here sigma A which is equal to sigma B. Sigma A means charge per unit area. What is the charge here? Q1. Unit area is, we can write capital A. So Q1 by A, here Q2 by B, second sphere. So surface area means 4 pi r square. So this radius is smaller, this radius is capital R. We can write here Q1 by 4 pi small r square, that equal to Q2 by 4 pi capital R square. See here, 4 pi cancel. What we get now here? See, I write here Q1 by small r square equal to Q2 by capital R square. See, we want to find out here Q2. Q2 equal to what? R square. We can write here Q1 capital R square by small r square. We get this is the relation Q1 Q2, sorry, Q2 equal to what? Q1 capital R square by small r square. It value substitute in equation 1 now. See here, Q1 plus, instead of Q2 we can write Q1 capital R square by small r square, that equal to capital Q. See, Q1 common now here, what we get? 1 plus R square by small r square, that equal to capital Q. So from this what we can write now? Q1 into small r square. LCM is r square, so that's why r square by r small capital R square by small r square, that equal to Q. See here, Q1 equal to what we get now here? Q capital Q R square by small r square plus capital R square. What is the Q1 value we are getting? This is the Q1 value. See here, Q1 equal to capital Q small r square by small r square plus capital R square. See now, so Q2 we want now, here see Q2 equal to, we can write, so Q2 equal to, Q1 means this one. See, I write here Q R square capital R square by small r square into r square plus capital R square. See, Q1 means this value, Q r square by r square plus capital R square. R square is there, like that only you can write R square. See, this R square, small r square cancel. What we get here now? Q2 equal to, Q2 equal to, what we get? Q capital R square by small r square plus R square. It is the Q2 value we get. This is Q2. See, Q2 value. Here Q1 value we get. So Q1, charge on first sphere, charge on second sphere we get. See once again, what now here? It is the concentric hollow spheres. So charge on first sphere is Q1, charge on second sphere is Q2. Total charge is capital Q. Q1 plus Q2 equal to capital Q. What they give condition? Such that their surface charge densities are same. What is the surface charge density of first sphere? Sigma A. Second sphere? Sigma B. Sigma means charge per unit area. See, what is the area for this sphere? Surface area 4 pi r square. Here 4 pi capital R square. 4 pi cancel. Q1 by r square equal to Q2 by capital R square. So Q2 we can write. So it will changes to here means Q1 capital R square by small r square, Q1 plus Q2 means here we know first equation Q1 plus Q2. In this one we can substitute this value Q1 plus Q1 capital R square by small r square into small r square. See here, LCM we can take now, r square plus capital R square by r square equal to Q. So from that Q1 value we get this. What is the Q1 value now? Here see, q1 value is capital Q small r square by small r square plus capital R square. So q2 value q r square by r square, small r square cancel, small r square plus r square. So q2 value this one. So what is the potential at the center of the this one now? From center to here surface, same potential. From center to here, same potential. Why? Because for conducting sorry, hollow conducting or non-conducting solid conducting spheres, center to surface, it maintains constant potential. So that's why for first sphere, what is the total potential at center? Na I write here first sphere k q1 by small r. So second sphere k q2 by capital R. It is the potential at center of the concentric hollow spheres. See, we can write here q1 value, q2 value. We get the potential at center. See, k q1 value na this one. So q r square small r square by small r square plus capital R square into here r is there. See, plus aq capital R square by see r square plus capital R square into capital R. Here see, one small r cancel, one capital R cancel. What we get now? Here see, finally we get potential at center of the concentric sphere is kq. We can write common here. What we get here? R by r square plus capital R square. Here capital R by small r square plus capital R square. See, here we can write potential at center equal to kq small r plus capital R by small r square plus capital R square. It is the electric potential at the center of the concentric spheres. What is the potential now here? So potential at C equal to kq small r plus capital R by small r square plus capital R square. It is the potential due to concentric hollow spheres, electric potential due to concentric hollow spheres at center. So what is that now? Vc equal to kq small r plus capital R by small r square plus capital R square. Okay na? So this is the electric potential due to charged spheres. See, I think it is very good concept. So please see my video, subscribe my channel and share to your friends. Thank you.